Hi everyone! In this installment of Programming for Lovers, we are going to take everything that we have learned about Monte Carlo simulation and build an election simulator. We will then apply our algorithm to real polling data from the 2016 US presidential election and run millions of simulations in order to estimate the likelihood of each candidate's victory at different points in time in the lead up to the election. As always, if you enjoy what you see, please like and subscribe. Plus, check your work from this code along and unlock tons more content at programmingforlovers.com. Let's code. To get started, we're going to put our code in the election folder that we started working with in the previous code along when we wrote some functions in io.go in order to read in electoral college votes as well as polling percentages from files. In this particular code along, we're going to put functions within main.go in order to simulate a presidential election from that polling data once we can read it in. So if you want to follow that code along, if you haven't already, go check out how to write those functions in io.go, or you can grab that file from our website. What I want to do is actually simulate an election. And in main.go, you'll see here is our func main from the previous code along. We're going to read in the electoral college votes and polling data from file. We're going to store them in as maps of state names to the electoral college votes of that state, or the polling percentage for candidate 1 in that state, which in this particular simulation will be Hillary Clinton from 2016. And currently we have a couple of print statements here that are just going to be printing those maps, but in this code along, we're going to actually run a simulation using those maps and then print out the probability of each candidate winning according to our simulation. So to produce our simulation, what I really want is the highest level function called simulate multiple elections. That function is going to runs a Monte Carlo simulation with multiple trials to simulate a presidential election. And so what it's going to take as input is a number of different things. It's going to need polling data as a map of states to percentages for candidate 1. It's going to need a map of state names to electoral college votes. And the electoral college is the collection of votes where each state is run as essentially its own election. You can check out our website for a longer explanation of this. And then whoever wins that state, it's winner take all. So the number of votes is proportional in some respect to the population of the state. So the larger the state, the more electoral college votes are up for grabs. But it's only all those votes for most states are won by one person. We have two more things in our input that we're going to have, and those two things are an integer corresponding to the number of trials that we want to run and a decimal margin of error. And that margin of error is going to apply to all of our polls, and it's going to dictate about how confident we are in those polls. I'll talk more about that later. In the meantime, I'm going to say that the output of this code is going to be 3 probabilities. And those probabilities correspond to the likelihood of each of the candidates winning. And you say, why are there 3? Well, there are 3 because we also could have a tie in the electoral college. So after all the states are divided up, you sum up all their votes, it could be the case that we obtain a tie. So I'll type all this out as our function signature. We have a function called simulate multiple elections. It takes our polling data as a map of state names to percentages. It takes a collection of electoral college votes as a map of state names to unsigned integers. And it's going to take the number of trials that we want to run as an integer, and it's going to take a margin of error as a float 64. And then we want it to return, as I said, 3 decimals, so 3 float 64s corresponding to each of those probabilities of candidate 1 winning, candidate 2 winning, or a dreaded tie occurring. Now you might think this is a lot to do to write this function. And one of the things that we're going to benefit from is to think about how we can be somewhat lazy and write this function in a fashion that's going to push the details of generating random numbers, and even in this case, simulating a single election to subroutines. I want to think on a very high level here, though, and think about what is it that I want to do. I want to run a bunch of simulated elections, and I want to keep track of how many are won by each of the candidates and how many are ties. So I'm going to declare 3 variables that are going to keep track of those. And then at the end, I'm going to divide the number of wins for each of the 3 possibilities by the number of trials. And that's eventually what I'm going to return. So I'm going to have a probability 1, and I need to be careful here. I don't want to do an integer division, but I want to divide win count 1 by the number of trials, casting to a float for each of those variables. And I want to have a probability 2. That's the same thing where I divide win count 2 by the number of trials. And then I want to do the same thing for the probability of a tie, which is the number of times we see a tie divided by the total number of trials. After I do each of those are the likelihoods that I want. And so I'm going to return probability 1, probability 2, and the probability of a tie. And we haven't really written a lot of complicated code yet, but this is nice to sort of start our function off with something we know how to do, think about what it is that we want to do at the highest level of the function. We want to keep track of these count variables, and then at the end, divide the count variables by the total. In the meantime, we have the meat of our function, which is to simulate a single election n times and update the counts. So as we go through this, I'm going to need a for loop that's going to start I as 0, I is going to go up to the number of trials, and I is going to increase by 1 each time. I's value here is not really relevant, but each time I want to simulate 1 election. So I'm going to need to write a subroutine. This is what I was talking about when I was referring to being lazy. We're going to have a subroutine called simulate 1 election, and it's not going to need number of trials, but it's going to take all of the other parameters to simulate multiple elections and just feed those down into this subroutine. So it's going to take the polls, it's going to take the electoral college votes, and it's going to take the margin of error, and it's going to handle the simulation of a single election. And then you might wonder, okay, great, we can do that. But then what is it that it should actually return? So we need to look ahead and start thinking about that. And I'm thinking, well, if I'm simulating an election, what is it that I really want to produce from this? I'm probably just producing the number of electoral college votes for candidate 1 and the number of electoral college votes for candidate 2. So hang on to that thought, but I'm going to return both of their number of electoral college votes and just store that as votes 1 and votes 2. And then I'm going to say, well, who won? And that's an easy check because it's just a matter of saying, is it the case that votes 1 is bigger than votes 2? And if so, candidate 1 won. So win count 1 needs to go up by 1. Otherwise, if votes 2 is bigger than votes 1, we need to say win count 2 went up by 1. And then the final case is the dreaded tie, and so tie count needs to increase by 1. And after we've done that, we realize that our function is now complete. Our function for simulating multiple elections has been written, and now instead of thinking about all running many trials, we just have to run one single trial and simulate a 1 election. So that's going to be probably a standard way of writing Monte Carlo simulations, and it's something that if you followed our craps code along where we simulated the game of craps and computed the house edge there, we passed the work to a subroutine that played the game of craps 1 time, and then we just called that function many times as needed. So we're doing the same thing here. We see sort of the same general principle arise, and this makes our work easy. So this way we only have to think of 1 task at a time. In particular, I'm going to say, okay, simulate 1 election. And it's going to simulate a single election from polling data. Okay. And then you're going to say, all right, what are the inputs need to be? And as I mentioned, they're the same inputs as for simulate multiple elections, but I'm just getting rid of the number of trials because I've already used that parameter as needed. So I'm going to have a func simulate one election, and it's going to take in those other three parameters. So I'm going to copy them down. That way they'll stay in the same order. And I'm going to get rid of num trials. And I'm going to specify that in the input as well. So I'm just going to copy my input from simulate multiple elections down as the input specified for one election. And I'm going to remove the number of trials there too. And then so you'd say, well, what is the output? And this is something that we already introduced. So we already specified when we called this function that we hadn't written yet, that it needed to return the number of electoral college votes in this simulated election for candidate 1 and the number of votes for candidate 2. So here we're going to say the number of electoral college votes in a simulated election for each of candidate 1 and candidate 2. And in this particular case, let's have those be unsigned integers since we have the electoral college votes represented as unsigned integers as well. Now we're ready to write this function. And in terms of writing this function, well, we want to return two unsigned integers. They're going to represent in this one simulated election the number of votes that each candidate obtains. So I'm going to declare college votes 1 as an unsigned integer and college votes 2 as an unsigned integer as well. And eventually that's what I'm going to return. College votes 1 and college votes 2. I could also have, if I wanted to be precise, that these are equal to 0. But as we know from our work with declaring variables, when we declare an unsigned integer, it will by default get the value of 0. Now for the meat of our function, what do we want to do? Remember, we're simulating multiple different elections here corresponding to each state, where each state is winner take all. So we want to range over all the states and simulate the election in each one. And there's a couple of ways that we could range over the states. We could range over the keys of the polls map, or we could range over the keys of the electoral votes map. It doesn't really matter. I'm just going to range over the polls. And I'm actually interested, as you're going to see, I'm interested in the polling value for that state as well, which is going to be the value associated with the state as I range through the polls. First, let's grab the number of electoral college votes. I'm just going to say EC votes there. And I can get that by saying, okay, I'm not ranging over the polls, but I know the current state name. And so I can get the number of electoral college votes if I access the electoral votes of that state. So I could say num votes is the electoral votes of state. And I'm just going to store that for now. I'm going to eventually use it based off of who wins the state. One thing I could do would be to say, well, is candidate 1's polling value here, is it greater than or equal to 0.5, or is it smaller than or equal to 0.5? And based off of that check, I would say, well, candidate 1 is either going to win the state or lose the state. But this would lose the whole spirit of Monte Carlo simulation. The idea here is that when we look at, say, our early polls, these numbers are not set in stone as the true polling percentage for each of candidate 1 and candidate 2 in that respective state. It's an approximation of the true number, and the true number we would think probably is within some range of the given numbers, but we're not going to say it's exactly equal to 47.21627 in Alaska and so forth. So for that reason, what we will do in terms of running a simulation is to add some noise to candidate 1's percentages. And so let's do that. You say, well, how are we going to do that? And I'm going to tell you, well, this is where anytime we come to a technical detail in computer science, a great idea is just pass it to a subroutine. let's be lazy. Adjusted poll is going to be equal to add some noise to the polling value. And here's where the margin of error is going to come in. So the margin of error is telling us with 95% probability, according to our estimation, if the margin of error is 10% and the polling value is 42%, then we think that with 95% probability, the true value of that poll is between 0.32 and 0.52, between 32% and 52% if the margin of error is 10%. Okay. So we're going to use that within the subroutine. I don't need to think about it more for now. For now, I'm just going to say, after I've assumed that that function works its magic, who won the state? And this is based on adjusted number. So after we've added a little bit of that randomization to it, we're going to check who won it. And the adjusted poll is for candidate 1. So I'm going to check, is it the case that candidate 1's adjusted polling percentage is more than 50%? And if so, candidate 1 won. And so we need to update the college votes for candidate 1 by adding the number of votes for the state, which I declared here just for the sake of simplicity and convenience, and add that into college votes 1. Otherwise, candidate 2 won, and I'm going to update its number of the candidate 2's college votes by adding the number of votes for the state into candidate 2's total. We're not dealing with ties here because we're assuming that a lot of people live in each state. We're not handling a tie. Similarly, I'm not worried as to whether or not I'm checking for adjusted poll to be greater than or equal to 0.5 or greater than 0.5 because we're going to be generating random decimals here, and the likelihood of that adjusted poll hitting 0.5 exactly is going to be so minuscule that it's not going to change the simulation tremendously. I will allow you to play around with this if you like. I'm going to leave it at greater than or equal to. That having been said, we've now written our simulate1 election function, so we're able to simulate a single election as long as we are able to write this add noise subroutine, which brings us to the next part of our code along, which is that we want a function called add noise that adjusts a polling percentage based on some randomization sampled from a normal distribution, and I'll talk about that momentarily. It's going to take as inputs 2 decimals, a polling value, and a margin of error. And what it's going to return is a decimal corresponding to the adjusted polling value. So we're going to have a function called add noise. It's going to take a polling value. It's going to take a margin of error. Both of those are floats, and it's going to return a float. And then the question is how to write this function. So as I mentioned, we're going to use the normal distribution here. And we said that with the margin of error, we want that margin of error gives us a 95% confidence that the polling value is within that range. So what I want to do is generate some variable x that's going to have some randomization built into it. And then at the end of this, I want to return x plus polling value. Okay. And what I want is for x to have a 95% chance of being between negative margin of error and positive margin of error. So if the margin of error is, say, 10%, then when I add in x into the polling value, there's a 95% chance that the resulting value is within the margin of error, within 10% of the starting value. I'm going to sample from a normal distribution in order to get this x. So I'm going to start off with sampling x as a norm float 64. So x has a 57% chance of being between -1 and 1. On average, x is going to have an average value of 0, but it could be larger. It's going to wind up being positive or negative in practice. Its standard deviation is 1. And at 2 standard deviations for this normal distribution, x has a 95% chance of being between -2 and 2. And that's different from what we want. We want it to have a 95% chance of being between negative margin of error and positive margin of error. So after we've generated x initially, I need to adjust it a little bit. So the first thing that I'm going to do is say x equals x divided by 2.0. Or I could have, as a shortcut, said x divide equal to 2.0, and now x has a 95% chance of being between -1 and 1. So I've just normalized it down. Now I'm getting really close to it being in the desired range. Here, I'm just going to say x times equals margin of error. And that's going to give us what we want. So at this point in time now, x has a 95% chance of being between negative margin of error and positive margin of error because I multiplied it by margin of error after it was between -1 and 1, 95% of the time. So for example, again, if margin of error is, say, 10%, most of the time, x is going to be between -0.1 and +0.1, and that's the value that we're going to add to the polling value to bump it up or down based off of random chance. You'll notice that I didn't call a subroutine other than this ran.norm float 64 function that's built into the ran package, and so we've now implemented the engine for our simulation, which is really cool. We can now run it in main and simply call these functions. So let's do that. That's the fun part. As I said, we've got code here to read in from the data folder our electoral votes and our polls. We're going to start off with, let's start with early polls.csv. So if we look at these 3 files, what we're going to see is that the values change over time. The early polls are taken from May and June in 2016. The next sample that we did was of conventions, which were around July 2016 when the national conventions were happening. And then we have the debates file corresponds to when the presidential debates were occurring in September and October in the lead up to the election in November of 2016. So we're going to run our simulation on each of these 3 files. We're going to start with early polls. We're going to go chronologically. And I'm not interested in printing out the maps that we have. We did that in the previous code along. Instead, what I need to do is, when you look at simulate multiple elections, remember it has these 4 parameters. And so what I need to do is, I've got my polls, I've got my electoral votes, but I need 2 more parameters. I need a number of trials, and we're just going to set that equal to 1,000,000. That'll give us a nice large number of trials without causing our simulation to run for a really long time. And the other thing that I want to do is set our margin of error. So let's start our margin of error as 5%. So 95% of the time, we can imagine that our polling value that we're getting from our file is within 5% of the true value. Now that we've got that, though, I can run our code. So I want to run simulate multiple elections. And as I said, it's going to give us these 3 probabilities. So the 3 probabilities are what are going to be returned by the function. And so I'm going to declare those 3 probabilities equal to the output of simulate multiple elections. And I'm going to give it polls, electoral votes, num trials, and margin of error. Once I've done that, it's just a matter of printing out those probabilities in a nice format to the console. So let's say probability of candidate 1 winning, and I'm going to have a comma, and then I'm going to print probability 1. And then let's print this again for candidate 2. And then we're going to say probability of a tie is that probability of tie variable. And once we've done that, we can save. I've probably got some compiler errors, who knows. But once we've got that, we can come in here and pull up the bottom. I'm going to try to pull up the bottom. There we go. And that gives me a terminal. And I'm already in the Go source code directory. So I'm going to cd into src election. And I'm going to compile. And that's going to compile both the code in main.go and in io.go. And if we had 40 Go files within this folder, it would compile all of them and produce one executable program that's going to go into the election folder named election, which is that file that you see there on the right. On a Windows machine, I can run that simulation with election.exe in the console. Here on a Mac, I'm going to run /election and execute that. And our election is going to be simulated. And you might say, well, what do we see? This is strange. We see like a 99.9% probability of a Clinton victory. Clinton here is candidate 1, Trump is candidate 2. That seems a little bit aggressive in terms of as an estimate. Now, it might be that candidate 1 was just that far ahead, but let's make our model a little bit more conservative, and let's set the margin of error to 10%. So that we're not as certain about this, so that it's possible that if the polling value is as low as 40%, it might be, say 41%, it might be the case, it's within the margin of error, that polling percentage could actually be 51%. And so a candidate that seems like they're behind significantly there might actually be winning, or might actually have a chance of winning the state in the future. So I'm going to update that to 0.1. Let's see how that affects our simulation. I think that's still a reasonably conservative margin of error. And now I'm going to compile our code again after saving and run the resulting executable file. And what you're going to see is that still we have a pretty significant likelihood of a candidate 1 victory. We don't need to recompile the code. We can run it again if we like and see that the law of large numbers is working here. We have about a 98.6 or 98.7% likelihood of a candidate 1 victory based off these data that we compiled in earlypolls.csv. So then the next question would be, all right, why don't we look at the other 2 polling files? Maybe things changed over time. So I can change this by changing my file name in the poll file to not early polls, but conventions.csv. Save it, compile my code, and run my code. And here we see that actually, and I'll run it again so you can see that the value is honing in there. Here, things seem to have indicated an even greater chance of a candidate 1 victory later on in the summer of 2016 with like a 99.3% estimation of candidate 1 winning. All right, well, let's go to the conventions. The debates. Let's get even closer to the election and just be a few weeks beforehand. We'll save, compile, and run. And here we see that actually, of all the 3 cases, this one is estimating with the greatest likelihood that candidate 1 is going to win. So here we have 99.5% or 99.6% of the simulations are coming back with a candidate 1 victory. This is weird. It's weird for a couple reasons. The main one is that it doesn't really agree very well with what major media outlets were saying during 2016. So all major media outlets were predicting a Clinton victory, but they were doing so depending on the publication, and this changed over time, with a likelihood of between 60% and 90%. But no one was saying that the likelihood of a Clinton victory was like 99.6%, especially right before the election. So you might be wondering, what's going on? Is our election simulator that we've created bad? And the answer is yes. And it's not because it's broken. And it's not because we've incorporated a bug. It's not because we're doing something that's much simpler than what some of these major media publications were doing in 2016. They have a few more bells and whistles on their simulations. So for example, they might take correlations between states into account so that if there's an upset in one state, it makes it more likely that there's an upset in a neighboring state or a state that tends to vote the same way in national elections in the favor of the candidate that produced the upset in that state. So there's more to it that we could add statistically here, but the engine for that simulation, if you looked into the guts of the code for one of these media publications, you'd probably see something that looks, on the whole, relatively similar to what we have produced, just with a little bit more code on top of it. The true answer is not that our model is bad. The true answer here is that really all of these Monte Carlo simulations, at the end of the day, for simulating a presidential election from polling data, stink. And you might wonder why. Everything here looks right. And the problem is we got really caught up in building the model, a model that I really always find fun to code, that didn't really stop to reflect on the fact that predicting the future is just hard. And polling data can be extremely squirrely and difficult to trust. And we were treating these as probabilities when really what we're doing is just running a model based off the polling data and seeing how often it comes back with candidate 1 or candidate 2 winning. We're not actually predicting the future, which is a much harder problem and something that really no one is capable of doing. If you don't trust me, ask your local weather person. All right. If you want a more thorough explanation of all this, I would say check out a section of our chapter that we have posted at programmingforlovers.com. I get more into details about the criticisms of these Monte Carlo simulations from polling data and how we might improve them or how we might reflect upon them. So go ahead and check that out. And then you're going to be ready to apply what you've learned throughout this chapter to complete some exercises on pseudo-random number generation, on Monte Carlo simulations, and have a little bit more fun. I'll plan on seeing you in the next chapter, but you've got tons to do before then, and I look forward to seeing you then. Until then, happy coding.